Okay, good afternoon everybody. Welcome to the webinar. My name is Guido Bregoli, and in 2014 I received a PhD in structural rehabilitation of historical and modern building from University of Brescia.
Sorry Guido, I'm interrupting you. I think now you can share your screen with us.
Okay, okay, sorry. Okay, perfect. Do you see my desktop now? Okay.
Yeah, perfect.
Perfect. And I'm working on the design of a steel bracing system, and in particular focusing on buckling restraint braces behavior. At the moment, I am a postdoctoral fellow at the University of Bergamo, where I'm studying the hysteretic behavior of RC structures, collaborating with Professor Riva, that is responsible of the present research. For further needs or information, you can find my email contact on the left corner. Okay, we can start. Today I will present the topic of my research regarding the design of an innovative construction system entirely made, as you can see from the first picture, with concrete, or better, as I'll show you in the following, with shotcrete, also called spritz-beton. In particular, the research was born with the aim at developing a simple construction method to realize sustainable residential buildings, especially social housing, and thus suitable for new emergent economies. The main features that we set out to achieve before starting were to realize a system characterized by high acoustic and thermal performance that provides for a considerable reduction, about 30% in the carbon footprint of the construction system, with respect to a traditional building where the building structure is made, for example, of traditional reinforced concrete and infill with hollow bricks. Our system has to be suitable for different places and thus reliable also in high seismic areas. And finally, a system that could guarantee ease and construction speed and thus economic advantages. So we have looked for a system very versatile and flexible, and that resulted adaptable in different contexts, both for social housing, but finally also for building with high architectural quality, and as said, reliable for the adoption in high seismic areas without any virtual limit to the number of stories. The project globally took more than 2 years, and several experts of different scientific areas have been involved to reach the previous goals. The University of Bergamo, in particular, as a scientific partner, was responsible for studying the seismic structural behavior of the design system, for assessing the thermal performance and the energy charge of a typological building, for evaluating the economy and financial aspects, and for investigating the competitive positioning of the technological system in Italy and in the developing countries. Along with University of Bergamo, private companies have been also involved. In particular, as industrial partners, they faced 3 specific different topics. The first one was to design and to develop the new constructive process, thinking on the structural layout, the wall layer, such as material, geometry, and so on. Another fundamental topic was the development of a specific mix design to obtain a reliable shotcrete capable to replace the traditional concrete. And the last contribute was to study specific temporary works to optimize the executive process. In conclusion, experimental analysis to assess the acoustic performance of the external walls and a study of the environmental sustainability by means of a carbon footprint analysis have been conducted. Speaking about the presentation, it focuses on the possibility to accurately reproduce with the IANA fan code the structural response of a typical structure realized with the proposed system. In particular, the presentation is composed by 4 parts. In the first one, an introduction to the research project is presented, focusing attention on the single module of the external wall. After that, in the second part, I quickly describe the experimental campaign carried out on 3 full-scale specimens. In the first section, I show the choices and the hypotheses assumed for the numerical analysis to reproduce the observed experimental behavior, highlighting the modeling assumptions and the proposed mesh. In conclusion, the numerical result compared with the experimental ones will be discussed. In this slide is briefly illustrated the pair chart regarding the conceptual map that governs the work. I will tell you only about the first two boxes. The first one concerns the methodology, the design, while the second one relies on the research and the development for the theoretical and experimental validation of the construction system. As initially reported, the main innovation is related to a new way of using the shotcrete. This kind of concrete is widely used in a lot of different applications. For example, we are used to see it in tunnel linings or for slope stabilization works. Another typical use is as a repair system for local intervention in a damaged structure. But in all these applications, the shotcrete is not the main constitutive element for the structure, and it is used as a layer of small thickness only with the aim at reinforcing a surface. Given the fact that shotcrete can be proven to excellently adhere to a support, and that usually show high mechanical strength, and that it usually results in a compact and homogeneous material, there are also many kinds of different systems that imply the use of shotcrete also in structural application to realize buildings. In this case, shotcrete is substantially always used as a lining layer of a limited thickness to realize a building where the insulation system is directly coupled with the bearing structures. In the first figure on the left, for example, the structure is composed by moment-resisting frames made of traditional concrete, while the infill are made of shotcrete directly applied on the EPS panel that operate both as thermal insulating material and as formworks for the shooting. Differently from the previous, other more standardized construction process use an integrated system based on modular insulating panels pre-coupled with a welded wire mesh and finished by a concrete casting. In this case, reported on the right corner, the building bearing capacity is given by sandwich walls obtained using the previous reinforced EPS formworks as a support for the shotcrete application. It's important to note that in this system it is essential to ensure structural continuity between the individual modules by providing constructive measures as the insertion of supplementary reinforcement or the overlapping of the wire meshes. In our proposed system, the bearing capacity instead is provided by seismic resistant structural elements made with spritz-beton that are more small RC walls widely spread on the perimeter of the building. Also, all the infill panels are made by using shotcrete, thus realizing a continuous lightly reinforced non-structural walls connecting the shear walls that have approximately 4 meter spacing, 4 meter to 6 meter. Differently from the previous system, the secondary elements do not fulfill any structural function and could be considered as simple infill panels without load-bearing role. Moreover, the proposed structure, being a traditional structural wall system, can be designed through a traditional approach, not requiring any kind of specific or special certifications. The use of shear walls coupled with a flat two-way reinforced concrete slabs leads to a simple overall structural system, which has the advantage of avoiding the complexity of the design and construction of seismic resistant frames, for example. The construction phase of each floor starts by positioning the shoring necessary to cast the upper slab system. Then the EPS panels are fixed to the base floor and to the upper shorings through proper devices. The main innovation consists in the layout and in the composition of the external walls. You can see in the figure. The construction system is constituted by prefabricated EPS elements, which are pre-shaped and customized, taking into account the presence of door or windows. Once the EPS panels are in place, following a simple mounting scheme, welded wire mesh is fixed to the panels and the wall reinforcement assembly of the structural walls is placed. The EPS panels act simultaneously as a support for the concrete during the spring phase, made by means of a spritz-beton wet method, and as an outer insulating layer during the building life. The last phase of each floor construction consists in the cast of the upper two-way slab, and so no beams or drop panels are required by the device system, thus ensuring the maximum ease and construction speed. After casting of the shotcrete for the structural wall, and if this is the case for a lightly reinforced non-structural panel, the wall section is finally completed by placing cladding panels on the inner side and by filling the inner chamber with proper insulating material, thus improving the thermal and acoustic efficiency of the construction system. To avoid uncertainties, a wet mixed method has been adopted. It provides for the pumping of pre-mixed cementitious composite, hence already mixed to the water in a storage container before entering the nozzle. In this way, the worker can compromise the mechanical characteristic of the final product, not being involved in the control of water addition. In fact, the mixture goes out through the nozzle thanks to the compressed air that permits the shooting on the APS panels without any additional operation. That results in a material whose mechanical properties are stable, replicable, and guaranteed. On the contrary, in the dry mix method, the cementitious mixture is blown through a hose to the nozzle, where the operator should add water. It results that the nozzleman should be very careful in choosing the right amount of water, avoiding to compromise the mechanical characteristic of the final product. In order to be able to cast all of the components without the use of traditional formworks, including the structural walls, while obtaining satisfactory and reliable structural properties for the concrete, a new fiber-reinforced shotcrete material has been developed to guarantee both workability and mechanical resistance, and to allow good cohesion between concrete and vertical supports. In this slide, the shooting phase during the preliminary test are shown. On the left side, one can see the material applied in correspondence of the infill. Instead, on the right side, a structural wall is casted. This is only first attempt, but the preliminary result gave us important information for the prosecution of the research. First of all, the worker have to pay attention to correctly regulate the amount of the compressed air flow. Otherwise, the impact forces become too high, and this can result in deflection or vibration of the support that can also imply a rebound and thus a wastage of material. This test, in particular, relies on the assessment of the feasibility of the process, monitoring initially the capacity of the cementitious compound to adhere to the supports and to show limited rebound. Considering that in this application the supporting surfaces acting as formworks are not stiff and don't have high inertial masses, they may be subjected to non-negligible vibration. In order to guarantee adequate stiffness, it's very important to choose correctly the thickness of the EPS panels and especially the spacing of the stiffness used to stabilize them during shotcreting. In this case, neither any delamination between support and shotcrete nor sliding between two consecutive layers of shotcrete have occurred. This is due firstly to the mechanical characteristic of the developed cementitious compound that as a result homogeneous and sufficiently compact and with a very good strength capacity. Moreover, the success of the preliminary test has been also reached thanks to the efficiency of the selected EPS panels, both in terms of roughness and of number of panel stiffeners. All these features has permitted to obtain a considerable thickness, in particular more than 20 centimeters, without wastage of material and permitting to progress with the experimental campaign. After assessing the reliability of different cementitious materials in terms of stability and absence of sliding phenomenon, uniaxial compressive tests on several cores extracted from the structural wall have been carried out and a maturation curve has been defined. Two different types of cementitious material have been tested during the preliminary test. The first one, named Mix 1, has appeared to be homogeneous in terms of mass density and reliable in terms of a structural response, reaching a mean compressive strength after 28 days curing equal to 50 megapascal, and especially showing an average strength at 24 hours equal to 28 megapascal, thus ensuring the possibility of erecting the structure with an extremely fast construction process. Concerning Mix 2, different problems regarding sliding between two consecutive shotcrete layers and detaching from the support have suggested to modify during the casting phase the mix by adding different types of plastic fibers. Nevertheless, the result of the test haven't proven to be up to expectations, thus suggesting to adopt the Mix 1 to proceed with the experimental campaign. To evaluate the seismic response of the proposed technology, a typical structural layout design with the proposed system as shown in the upper figures. The plans represent a model story of a 5-story sample building, specifically designed to investigate also the environmental impact in terms of equivalent CO2 and the thermal performance. The project permits also to derive a geometrical model representative of the real structure. In particular, 3 different specimens were grabbed from the external envelope of the building as reported in the slide. This to study the hysteretic response of the design structure and to investigate the interaction between infill and structural shear walls. The specimens have the same dimension and differs only in respect to the presence on a light infill panel that can also present an internal window opening as depicted in the slide. So each sample was made of an outer frame having an overall dimension equal to 4 for 2.88 meters, and they are composed of 2 external structural walls of equal size, 80 for 20 centimeters, connected at the top by a beam simulating the top floor slab, and at the bottom to a rigid foundation. The specimen wall 2 and wall 3 differ from the first specimen by the presence of a shotcrete infill panel, having a variable thickness between 2 and 6 centimeters. The specimen, being a typical portion of the external building envelope, are only constituted by the EPS panels and by the shotcrete layer. So, 3 pseudostatic cyclic tests have been conducted on the previous fuse-case specimen. The experimental tests have been performed imposing a displacement to the top beam by means of an electromechanical actuator connected to a rigid wall used as a reaction structure. To ensure that the wall deforms, avoiding lateral instability or out-of-plane displacements, a retaining system composed by 4 steel struts has been set up to guide the specimen during the load application. Letter C in the image. The rigid foundation has also been pre-stressed to prevent any possible slip phenomenon, and moreover it has been tied to the reaction floor close to the external sections, exerting a vertical confinement that inhibits its rotation and then its lifting. All tests have been carried out by applying a cycle displacement of increasing amplitude to the top beam according to the loading history shown in the table and depicted in the figure. The first level of the imposed drift equal to 0.1% is functional only to verify the elastic stiffness of the structure. After that, the loading history provides the execution of drift level multiple of 0.25% until reaching the imposed drift coinciding with 1% of the story height. From this step forward, the amplitude of the cycles is incremented each time by a value equal to 0.5% up to the collapse of the structure. In particular, for each drift level, 3 complete cycles have been repeated. As briefly outlined, the adopted protocol has been performed by monitoring the displacement in terms of interstory drift. The horizontal displacement has been registered at the top, in the middle of the upper beam, by the instrument named 2 and 27, while the height of the structure has been assumed as the distance between the point of the applied load, labeled 1 in the picture, and the base of the structural walls, in this case equal to 2.73 meters. The displacement, crack openings, and other kinematic quantities have been recorded during the test by means of a potentiometric transducer according to the layout shown in the figure. In particular, the device is located at the interface between the shear walls and foundation, and between the structural walls and the upper beam, have permitted to monitor the respective sliding, giving important information also for the numerical modeling. In this picture, that is the last regarding the experimental campaign, the specimen geometry and the reinforcement details are shown. As you can see, the spacing of the bar and of the stirrups is very repetitive, highlighting a regular layout. In particular, you see here the reinforcement designed for the upper beam, the one related to the structural walls, and the infill panels armed only with a light 15 centimeters wire mesh with a diameter 5 millimeters. Finally, the foundation has been designed to be over-resistant, and for this reason it was strongly armed to behave elastically. It's also important to note that sheets of electrowelded wire mesh are only placed side by side. In this way, the infill result attached to the remaining structure thanks to the wire mesh that goes on only over the structural walls. This layout has been responsible of the mechanism affecting the infill observed during the test. In fact, in correspondence of the shrinkage crack developed in the middle of the infill panel, the central panel tends to divide into two halves. The numerical analysis have been validated in terms of capacity curve, such as base shear versus interstory drift or displacement, and comparing the experimental crack pattern with that called numerically, trying to simulate and investigate the interaction between fill and structural shear walls. All the tests have been described with a two-dimensional model using only plane stress elements. The numerical simulation takes into account only the material nonlinearity by means of a smear crack approach, while the geometric ones have been neglected. Moreover, for the sake of simplicity, only monotonic pushover analysis have been performed, reducing also the computational cost about to 4 or 6 hours. In this way, the damage accumulation due to the cyclic actions has been ignored. Not having a specific characterization of the material except for the mean compressive strength, the problem has been studied from an engineering point of view, trying to reproduce the main mechanism observed during the test. In this way, it doesn't represent the validation of the specific material mechanical behavior. The proposed numerical simulation are performed by means of two-dimensional models where all the geometrical parts are meshed using 8-node quadrilateral plane stress elements. The mesh shown in a figure is highly structured, regular, and with square elements having side equal to 50 millimeters. As shown in the picture, only for the last test, Wall 3, in order to smooth the edges of the window, 6-node triangular plane strain elements have been used, placing them in correspondence of the corner of the window to avoid numerical problem due to high stress localization. Moreover, trying to reproduce the interaction between the parts making up the specimen, interface elements having zero thickness have been adopted. As shown in figure, 3 different kinds of interaction have been modeled. All the interfaces are only elastic, and in particular, the ones highlighted in red simulate in a simplified way the sliding occurring between the shear walls and both the top beam and the rigid foundation. These tools try to take into account the double action guaranteed by the longitudinal bars in correspondence of the construction joints. In this way, the sliding observed during the test can be modeled elastically on the basis of experimental measurements by means of an equivalent stiffness. This device also permits to reproduce numerically the correct value of the elastic stiffness registered for wall 1. On the contrary, neglecting this sliding phenomenon, the finite element model tends always to overestimate the stiffness of the structure. The interfaces between the infill and the outer frame, highlighted in blue in the figure, have the function to allow for relative movement between the bearing structure and the infill panel, given the fact that no reinforcement bars connect the parts except for the wire mesh. The most important interaction is the interface located, as previously explained, between the 2 halves of the infill along the center vertical line, the green one in the draw. In this case, the will was to replicate the formation of the sliding vertical surface due to the interaction of the wire mesh. In fact, during the test, increasing the external displacement, the pre-existent shrinkage crack along this direction become wider, causing the 2 halves to behave as 2 distinct parts, almost completely independent and connected each one only to the closer shear wall. Regarding the modeling of the reinforcement, as previously briefly described, all the horizontal and vertical steel elements having a regular spacing have been modeled as reinforcement grids. Thus, the reinforcement has been modeled as fully embedded in the concrete elements, implying a perfect bond between the reinforcement and the surrounding material. Firstly, it's necessary to define the area of the mother elements, and in particular, the following zones have been detected. The beam reinforcement 1, the foundation reinforcement, the area related to the longitudinal bars of the confined zone inside the structural walls, and in the same way, the one connected to the stirrups. After that, the areas for the wall shear stirrups and for the wire mesh have been created. Secondly, for each of the latter areas, an equivalent thickness for both global direction has been defined. Only as an example, to calibrate the geometrical property of the wire mesh, it's only necessary to divide the area of the bar cross-section for the wire mesh spacing. So being 20 square millimeter the area of the cross-section of a single bar and 150 millimeter the wire mesh spacing, the equivalent thickness result identical in X and Y direction and equal to 0.131 millimeter. In the same way, knowing the percentage of longitudinal reinforcement, it's enough to multiply the latter for the host element thickness. For example, being 1.64% the reinforcement percentage of the confinement zone, the Y equivalent thickness result equal to 2.463 millimeter. So, following this example, the X and Y equivalent thickness have been calculated for all the previous areas. In this slide, the different materials implemented in the model are presented. In particular, 3 distinct types of concrete have been defined. The traditional concrete used in the top beam, the shotcrete used in the structural walls and in the infill, and finally the ordinary one used in the foundation. In particular, acting as a rigid base, the foundation has been modeled as an elastic element, ignoring the material linearities. Nonlinear property in tension using a total strain rotating crack model being defined both for the spritz-beton and for the top beam concrete on the basis of the linear softening tension stress-strain relation, for which it is necessary to specify only the ultimate tensile strength and strain. Regarding the compressive behavior for the fiber-reinforced sprayed concrete, the parabolic diagram stress-strain model was used. In the latter, the data input corresponds to the ultimate stress and to the compressive fracture energy. To describe the compressive behavior of the ordinary concrete, instead, the Torrenfeld model has been chosen, defining only the maximum compression stress. Finally, given the fact that the infill panel isn't homogeneous in thickness and in density, the related material has been modeled, strongly decreasing the mechanical property of the structural wall shotcrete, as shown in the next slide. Both for the traditional concrete used for the top beam and for the shotcrete, a Young module equal to 20,000 megapascal has been adopted. Even if this value is lower in respect to the one suggested by the code for high-strength concrete as the present shotcrete, it is worth to remember that being a shooting and not casting, the actual cementitious material can be treated more as a traditional concrete, given the fact that the voids occurring during the shooting phase can affect also its stiffness. For the same reason, the ultimate tensile strength and strain have been hypothesized to obtain a tensile fracture energy more similar to that of a traditional plate concrete. Moreover, concerning the behavior in compression, the value of the fracture energy is very difficult to calibrate, affecting in a very strong way the ductility capacity offered by the structure. Despite that, it results that values between 10 and 50 kilojoule per square meter can be suitable to describe the experimental results. Regarding the ultimate compressive strength, the value listed in the table are coherent with uniaxial compression tests performed on all the above material, resulting in an average ultimate strength respectively equal to 50 megapascal for shotcrete, 15 megapascal for the top beam, and 30 megapascal for the foundation. As also reported in the previous, the interface mechanical properties have been calibrated basing on the experimental measurements. Interface elements have been provided between each structural wall and the respective top beam and foundation. A reduced value for the tangential stiffness has been calibrated according to a stress displacement relationship, taking into account the double action of the longitudinal bars. In this way, it was possible to reproduce in a simplified way the horizontal sliding observed in correspondence of the constructional joints. Moreover, interface elements have been implemented along the entire perimeter of the infill so as to reproduce the limited degree of cohesion with the outer frame. In this case, the tangential stiffness has been increased, taking into account that the infill result is confined by the external structure, such as the outer frame. Finally, a further elastic interface imposing stiffness values practically equal to 0 has been inserted also in correspondence of the center line of the infill to catch the relative sliding movement between the HUDs. Concerning the steel reinforcement, it has been decided to adopt a von Mises model with no hardening and a yield strength equal to 500 megapascal, thus describing an elastic perfected plastic material. This is the last slide regarding the finite element model, showing the applied load and the boundary condition. All the simulations have been performed applying a displacement of 1 millimeter amplitude to the center point of the top beam. Then a pushover analysis up to 60 steps have been carried out using both displacement and force control with a tolerance of 1% for both parameters. To properly simulate the load condition, the displacement has been applied at the top, connecting through a rigid link all the nodes belonging to the horizontal axis of the upper beam. This solution will constrain only the horizontal global displacement x-axis, causes the top beam to move rigidly and allows for a better distribution of the external load, thus avoiding a numerical problem, possibly numerical problem, due to the localization of high stresses only in a few nodes. Finally, regarding the boundary condition, the nodes belonging to the baseline of the foundation are simply constrained by means of hinges that inhibit both horizontal and vertical displacement coherently with the experimental setup. For what else? For each of the three tests, the comparison in terms of load displacement curves are presented, and in particular in the next slide, with the black line is reported the envelope curve derived from the experimental cycle loading. As previously said, the numerical simulation is only monotonic, and so in red is the capacity curve equal for both the direction given the symmetry of the specimen. These figures show first how for wall 1 the numerical result exhibits a good match in terms of elastic stiffness. The model seems to be also able to correctly catch the peak load, in particular 282 kN and 264 kN for the experimental test and 279 for the numerical one. The main differences are recorded in respect to the negative direction, but this evidence is only due to the cyclic effects. In effect, as you can see for each step of displacement, the experimental forces in positive direction are higher than the equivalent in the opposite side. This behavior is consistent with Bausch-Singer effect that implies a reduction of the yield strength, inverting the verse of the imposed displacement. Regarding the softening branch, after the peak load, a key role is played by the parameter of the compressive fracture energy that affect the ductility level provided by the structure. In this case, a value of 50 kJ per square meter has proven to be reliable. However, for wall 1, the seismic response seems to be very symmetric, and overall the capacity curve obtained from the finite element analysis is able to simulate with high approximation the structural behavior exhibited by the specimen. Okay. In this video, the deformed shape assumed by the specimen with the increase of the applied displacement is shown. The deformed shape is amplified 4 times, and the crack strains that occur on the structure are presented. The crack pattern observed for wall 1 is highly symmetric, with ample cracking zones which affect the bases of both structural walls, and with the formation of plastic hinges at the ends of the top beam. In this way, once the structure reaches its ultimate bearing capacity, it can be noted that the top beam is able to guarantee a coupling action between the walls. From this figure, you can see as the numerical simulation is able to describe the main structural mechanism, highlighting with good reliability the cracks that affect the structural walls at their base and that have been also responsible of the structural collapse occurred at 2.5% drift. Trying to compare the crack layout observed during the test with that provided by the numerical analysis, in this slide the cracks appear during the application of the load only in positive direction and in negative direction have been distinguished. In particular, in the left image, the load is applied in positive direction, from right to left, as also deducible, watching the orientation and the localization of the cracks. On the contrary, the picture on the right side shows what has happened during the application of the displacement in the negative direction. The picture highlights the superimposition between the experimental crack, black lines, and the cracked area caught numerically. As you can see, the model has proven to be reliable in reproducing the experimental behavior, also catching the inclination and evolution of the cracks. Both at the base and in correspondence of the upper beam, the crack zone caught numerically are a little underestimated, probably due to the cyclic effect that increase the damage level at each step and that here are not taken into account. The present slide, where details of the main cracks observed during the test are shown, confirms how the finite element model is able to reproduce the actual damage. In particular, in figure, you can see the detachment at the interface between shear walls and the foundation, and also the fractular cracks at the base that have been responsible of the collapse of the structure. Both the shear walls have experimented a similar damage pattern that involves about half of the height of the wall, as shown in the image A and B. Finally, observing the lower side of the beam, it is possible to recognize the horizontal cracks that signal the formation of a plastic hinge at the end of the top beam, later see in the figure. Speaking about the structural behavior observed for the specimen wall 2, the same graph load versus displacement, also proposed previously, is now shown. In this case, the prediction is less performing. Nevertheless, the results are quite satisfactory. In fact, the numerical curve appears to be consistent and quite similar to the envelope one, in particular concerning the stiffness during the elastic phase. The maximum load, equal to 391 kN, was reached for an imposed drift of 0.58%. This represents a mean value between the maximum and minimum peak load observed experimentally, respectively minus 7% and plus 8%, compared with the higher positive and negative value of the strain capacity observed imposing a drift equal to 0.5%. This confirms that the contribution in terms of stiffness and strength due to the presence of an infill plays a key role for the correct modeling of the seismic behavior of the tested structure. The offset observable between the two softening branches is probably due to the cyclic actions that affect the structural resources at each cycle. Although the numerical analyses are not able to perfectly simulate the observed progressive strain degradation, the model appears efficient in synthesizing the structural response, giving a reliable indication of its bearing capacity, both in terms of ductility and of maximum residual strength. Okay, as previously done, the video of the deformed shape evolution with the increasing of the ply displacement is reported, highlighting the zone affected by cracks. It can be noted how the infill panel tends to quickly exhaust its structural resources, highlighting, starting from 0.5% drift, widespread damage and significant cracks at the interface with the structural walls and along the edges with the outer frame. Observing the figure, it can be seen how at the base the cracked area is extending in height due to the presence of an inclined strut that develops within the infill. Regarding the outer frame, a crack pattern non dissimilar from the previous one can be recognized, except for the damage zone affecting the right shear wall due to the contribution of the compressive struts. The infill panel presents a crack pattern that appears similar between the two halves. This is due to the presence of the elastic interface with no stiffness model along the center line, and that permits to the two substructures to behave as independent parts. Moreover, it can be seen how once the central panel becomes inactive, most of the externally imposed loading action affects only the structures composing the frame. As usual, the superimposition between the experimental crack pattern and the numerical one is now presented, is distinguished between what has been observed during the application of the semi-cycles in positive and in negative direction. The result of the superimposition is very satisfactory, proving that the analysis is able to reproduce the different mechanisms. Here is possible to see the differences regarding the damaged area at the base of the shear walls. The first appears mainly cracked due to the bending moment contribution, showing cracks with regular spacing arising horizontally from the outer edge of the wall and tending to develop downwards thanks to the contribution of the shear action. In the second wall, instead, it can be seen how at the base the cracked area is extending more in height due to the presence of an inclined strut. In fact, you can see how the cracks have an oblique orientation and that follows the principal compressive stress trajectories. Also in this case, the extension of the damage zone towards numerically are underestimated, but the result can be considered as quite satisfactory, given the difficulty to properly describe the interaction between the outer frame and the infill.
Sorry, Guido. It seems there is a connection problem. Your voice is not really clear. Just to make sure that there is nothing over there affecting your presentation. Thank you.
I'm sorry. Okay, I try to be closer to the laptop.
Thank you.
Okay. Yes. Also in this case, the finite element model has proven to be able to catch the main mechanism observed during the test, especially correctly assessing the contribution in terms of bearing capacity offered by the infill. The choice to model the initial shrinkage crack as a plane of weakness revealed to be efficient in reproducing the interaction between infill and structure. Thanks to the presence of the central interface, the simulation has been able to reproduce the sliding phenomenon occurred between the infill halves, as highlighted in the picture with the red arrows. In this way, the infill tends to become inactive very quickly, and vertical and horizontal cracks appear along the perimeter of the panel. Regarding the shear walls, we can recognize damage very close to the previous one, with detachment at the base along the construction joint and cracks affecting the first 50 centimeter in height, due to the combined contribution of shear and bending action. Finally, plastic hinges can be recognized at the end of the top beam, as happened for specimen wall 1. Finally, the last comparison in terms of load displacement curve is presented concerning wall 3. The numerical predictions are in substantial agreement with the experimental evidence, both in terms of initial stiffness and peak load. The maximum force obtained for 0.65% drift is equal to 371 kN, respectively 2.3% and 14.5% higher than the experimental values, registered as usual at 0.5% drift. The trend of the softening branch is representative of the real structural behavior. However, it's interesting to note that the slopes of the two degrading post-peak branches tend to slightly diverge. The reason for this trend may be related to the greater damage suffered by the structural walls due to the stiffening effect exerted by the infill portion coinciding with the spandrel under the window. This configuration tends to reduce the slenderness of the walls and thereby inducing high shear stresses. Coherently with what done for the previous test, the evolution of the damage zone in terms of crack strain is reported, being in red the areas affected by strain higher than 3%. The deformation shape also in this case is amplified for time. The crack evolution reveals that from 0.65% drift, the infill panel is entirely damaged, and that the layout of the cracks appears stable and uniquely defined. The numerical model revealed to be extremely accurate, turning out to be able to capture both the sliding mechanism that occurs between the two infill halves and the main damage. As also reported in figure, the widest crack develop from the corners of the window along the construction joints and between the infill and the walls. Contextually, the outer frame presents a crack pattern very similar to the one related to the first two walls. The result of a superimposition between numerical prediction and experimental cracks in the hypothesis of a monotonic action confirm the potentiality of the proposed model to describe the main mechanism, highlighting at the same time the drawbacks previously mentioned. Also in this case, in fact, the shear walls are affected by a more extensive damage in respect to what's called by the finite element analysis. With respect to wall 2, the shear walls seem to be affected by cracks along their entire height, confirming that the presence of the inferior spandrel slightly affects the crack pattern of the structural walls due to high shear stress, as in a short column effect. Despite it, the last slide shows without any doubt the efficiency of the proposed modeling, comparing the distribution of the cracks, of the strain crack with an image of how wall 3 looks at the end of the test. The similarities are very interesting. First, with letter A, we can recognize the cracks starting at the base of the shear wall close to the foundation. In the same way, the letter B highlights the damage involving the right wall, where the cracks appears to be less pronounced, probably due to the action exerted by the compressive strut. As usual, close to the opposite corner of the window, letter C and D, important damage areas can be recognized, also clearly highlighted in the experimental view. Finally, also in this case, the sliding movement between the infill halves is correctly modeled, as shown in the upper image, where a detail of the window is reported. The experimental results have shown that the presence of an infill element affects the structural behavior only for low drift levels. With the increase of the imposed displacement, the hysteretic behavior tends to degrade toward a stable scheme made only of shear walls, and thus not vulnerable to brittle collapse such as soft story, and capable to exhibit ductility levels compatible with those suggested by the current seismic codes. In fact, a behavior factor equal to 3 can be assumed in accordance with the guidelines provided by the Italian code for structure with unpaired shear walls. Concerning the behavior at the damage limit state, it is also interesting to note that for cycles at 0.5% drift, No significant cracks on infill panels have been observed. Up to 0.5% drift including, the story shear values have been always increasing, and the first relevant structural damage affecting the infill has been recorded only during the cycles at 1% drift. Even at the ultimate limit state, the infill panels do not seem to have suffered deformation such to cause their collapse. The welded wire mesh, despite not being superimposed in the central part of the infills, has been able to retain the connection between the main structural elements and the concrete infill slab, preserving its expulsion. The out-of-plane mechanism shown by the two halves of each infill panel has appeared to be limited and not such to affect the stability of the external lining layers. In fact, the EPS insulation panels appear still globally intact and not detached from the structure. In conclusion, the numerical models has proved to be able in reproducing the main structural mechanism, resulting a valuable tool to describe the structural response of several models, and thus resulting reliable also for the study of different geometrical configuration. So I've finished it, and I think that's all. And thank you for your attention.